try it again, otherwise okay, let me try it again. Sorry, I lost the connection, and hopefully now it will not create any of the problems. So we were discussing first question. So we are going to solve a total of 4 questions, and the first question states that a child's hoop of mass m, radius b, rolls straight ahead with a speed v without slipping. The top of the hoop is given a light sideways tap at right angles to its direction of motion using a stick. The impulse of this tap is I. If the hoop is spinning very fast, the effect of the tap is only to change the direction in which the hoop rolls by a small angle phi. Find this angle phi. And part B, find the condition on the maximum force F of the tap so that the assumption in part A remains valid, meaning the tap changes only the direction of the motion and does not significantly affect the spin. So here basically we are given a, you can say, circular hoop, and that is, first it is moving in a straight line, and then a small tap is given so that it rolls, start moving in the circle, and it is going to bend by angle of phi. So we are interested in this, finding out this angle phi. So in this case, let us assume that if this is a plane and we have our hoop, which is suppose at a certain angle, and in this case we can assume that the 3 axes can be assumed at that we have our x-axis and we have our y-axis, and finally we are having our z-axis that will be perpendicular to both x and y. And initially the hoop was traveling in a straight line like this. When it is given a gentle tap, it starts to move in a circle. It is going to follow some circular path like this. And so if we draw this figure, same figure from the side, so let us suppose this is the circular track it is going to follow, and this is our hoop, and B is its radius, and this is the axis, and so this is a initial axis and it will be bending through angle, and that angle is given as our phi. So this angle is our phi angle, and it is also given that initially it was moving with the velocity of our v. So we consider the three vectors, and we considered that our y-axis, it is the original direction of the motion, original direction of the motion when it was traveling the straight line. And then we have our x-axis, and then x-axis is nothing but our lateral direction or direction of the impulse, lateral direction, or we can also call it as a direction of impulse, and this impulse is in this direction. Okay, and impulse is given as our I. And finally we are having our z-axis, and z-axis is nothing but normal to the hoop plane, normal to hoop plane. Therefore we can say that position vector of the top point relative to the center, because this impulse is at the top point, and if b is its radius, therefore we can say that the position vector will be equal to b and k unit vector, because it is in z direction. So you can say position vector of the top point relative to the center, and let us call this position vector as r. Then this r will be equal to the radius and our k unit vector. Okay. And also we can find out the impulse vector. We have our impulse vector, and which is applied at the top. So this impulse vector is our once again that is our an I unit vector. Therefore we can say that moment of inertia of the hoop spin axis, which will be through the center and normal to the plane. So we can say the moment of inertia about the hoop's spin, which will be through the center and normal to plane. And let us call this as moment of inertia. We can call this as I perpendicular, and that will be equal to mb square. And there is rolling without slipping. Rolling without slipping. Therefore, we can say omega is equal to V upon B. It is rolling with the angular speed of omega, and V is the linear speed of the center of mass. Therefore, we can write that the initial spin angular momentum let us call this as our LS, will be equal to our angular momentum L, and we have this as a J unit vector, and this angular momentum L will be equal to our I perpendicular multiplied by omega, and we know our I perpendicular, it is B square, and this is our V upon B. So here B and B cancels out, so this comes as our MBV. And for this is a vector notation, and this is magnitude notation, so this will be LS. So this we get our MB multiplied by V. Now we come to the deflection in the angle, and this deflection in the angle we can one second. Okay, so the deflection in the angle, we can write that our phi will be giving us for that we can say our deflection angle phi, and we can find out. For that we are required to find out the angular impulse about the center. So we can say that our angular impulse about the center, and let us call this as delta of L, and that will be equal to our R multiplied by our I. Okay. And we can write that delta of L is equal to R is our B of K, and I is our I of J unit vector. So this will be becoming a minus B I unit vector. Okay. So this will be our x component, and we are interested in magnitude, so we can simply write it as B of I. And after the impulse is applied, we can also find out the total angular momentum. After impulse total angular momentum, and let us call that total angular momentum as our LF. So we can say that our LF will be equal to angular momentum of spin plus angular momentum because of this impulse. So we get this as minus B of I plus mv j unit vector. Okay. And the tilt, that is our phi angle, is, you can say, away from the y-axis. So we can say the tilt phi of the total angular momentum, that is LF, is away from y-axis. Therefore, we can write that a tangent of phi will be equal to the magnitude of our L, which is our x component, and our spin component. So which in this case B of I divided by mv, and here this B and B cancels out, so this comes as I upon mv. Okay. And if this phi is very small, so from here we can say this phi will be equal to approximately I upon mv. And the part B, it asks for what will be the criteria of our maximum force, and say that our part B, and in this case we can say that the added angular momentum must be small compared with the initial spin angular momentum. Okay. So we can say that our delta of L, which is our B of I, should be much less than our spin angular momentum, which is nothing but our m times v. And from here we can say that our I should be much less than product of the mass and velocity. And if we are having because there is an impulse for the shorter time, that is delta of t, therefore we can say that our I is equal to 1/2 f multiplied by t. So we simply substitute it, we get this as 1/2 f delta of t is much less than our mv. Therefore from here we get that f should be much less than twice mv and divided by delta t. So this is the condition for our force. Next question. It states that a uniform thin rod of length L and mass m is hinged at one end of the roof of a car. The car is accelerating forward with a constant acceleration a. The angle between the rod and the roof of the car is theta. So based on this, we have two questions. Find the angle theta at which the rod stays in equilibrium when the car accelerates. Part B, if the rod is slightly displaced by a small angle phi from its equilibrium position, describe its motion for the small phi. And for this, we can just draw an approximate figure. And suppose this is the roof of the car, and we are having a rod that is hinged at the roof of the car, and here it is making an angle of theta, and it is given that the car is moving, accelerating forward direction with a. Okay, so the car is accelerating by the acceleration a. Therefore, there will be a pseudo force that will be acting on the rod, and suppose this is the center of mass. So here we are going to have our Fg, which will be nothing but our mg in the downward direction, and we are going to have this pseudo force. Let us call this as Fp, and that will be equal to our m times a, okay, magnitude otherwise, okay. And so the length of this is given as L. Therefore this center of mass will be the length of our L by 2. So this is our center of mass. So this is our initial condition, and it is given that this rod should be in equilibrium, and there are only two forces that are acting on it. One is our Fg, other one is our Fp. So they should be able to balance this particular rod. Okay. So obviously we are going to draw the, you can say, component wise for the forces, and we can also from here we can also draw the downward direction. We are having G, in the backward direction we have our A. Therefore there will be a G effective, and this G effective should align with the rod. Then only this rod will be in equilibrium. Okay. And in terms of vector notation, we can say that our G effective will be equal to our G minus A. And let's find out. Okay, and we are going to divide these two into the respective components, and so these two forces are going to produce torque in this rod. Okay, so this is our rod, and the torque produced by these two components, these forces, should be able to balance each other. Okay. So let us draw the components. So this is our rod, and we are having angle of theta. In the downward direction we have our mg. Therefore this angle will be over theta. So we get this as mg cos of theta, and this will be over mg sine of theta, and the center of mass is at a distance of over L by 2. Therefore the torque, because of our gravity, you can write torque due to gravity, and that torque, let us suppose, is our tau g. Then this tau g will be equal to our force, perpendicular force, that is our mg cos of theta, and multiply by the lever arm, that is our L by 2. It is given capital L. So this is our capital L by 2. So this is our torque due to gravity. And now we come to our this pseudo force. So this angle is theta, and pseudo force is acting in this direction, that is our MA. And we can divide this into two components. And this angle is theta, so obviously this angle will be also theta. So we are going to have this as our MA sine of theta, and the other component will be our MA cos of theta. And once again, the distance is our L by 2 because it will be at the center of mass. Therefore, we can say that the torque due to pseudo force let us call this as tau p, then this tau p will be equal to, we have our MA sine of theta multiplied by the lever arm L by 2. And at equilibrium, these two forces should balance each other, or we can say they should cancel each out. So we can say that for equilibrium of the rod, we should be having torque due to gravity should be equal to torque due to the pseudo force. And we substitute them. Torque due to gravity is mg cos of theta L by 2, mg cos of theta L by 2 is equal to MA sine of theta and our L by 2. And here this mass and mass, length cancels out. So we get this tangent of theta is equal to G upon A. Okay. Or we can say the equilibrium angle which we are supposed to find out, that is with theta, is equal to tangent inverse of G upon A. And mind it, this angle is with respect to the horizontal. Okay. So this was our first part. And in the second part, it is said that the rod is displaced by a small angle of phi. Okay. So we have a part B, and we are given that the rod is displaced slightly by angle phi. Rod is displaced by small angle phi, okay. And a small angle phi from the equilibrium, so which basically means that the equilibrium has been disturbed. Okay. And for that we can draw an approximate figure also. So under the equilibrium position, the angle was given as theta. So this is our angle theta. Okay. And in this case, under equilibrium position, we were having our mg, and this were our MA. Now we have disturbed the equilibrium. Suppose this is a new position and this angle is given as phi. Therefore, we can clearly see that as the rod is going to rise, the center of mass is also going to shift. So here we are going to get now our MA at this position. And so as this in previous part we said that the G effective, that is our, should be in this direction. Okay. And so we can call this our G effective. And when it is disturbed, the G effective is also going to shift its position. So it will be, because for the rod to be equilibrium, the G effective and the rod should align with each other. Now we have disturbed the equilibrium. Okay. So this is our A, B, the original position, and this is our A, B prime, that is a non-equilibrium position. So under non-equilibrium position, this G effective will be not aligned with the rod. Okay. So it will be at angle, and this angle will be our phi. And now we can find out our this what can I say, we are once again going to find out the resolve the components and get the solution. So for, like we said, that it is small angle from the equilibrium, therefore, and there will be storing torque, it will try to move the backward direction to its equilibrium position. So there will be a restoring torque. Restoring torque. And let us call this as tau rho. So tau rho will try to move it into back to its equilibrium position. Okay, that's the basic. And we are interested in this tau rho. Okay, and let me redraw this figure. We are only interested in this A, B prime. And we are having, this is our center of mass, and this is our net force now, that is our mg effective, and we can divide this G effective into two components. Okay. And this angle we said is our phi, so we can divide this into two components. One will be the perpendicular, which will be m G effective sine of phi, and other one will be our slightly and that will be our mg effective cos of phi. Therefore, we can say that our restoring torque, that is our tau r, will be equal to L by 2, and this comes as our m G effective and sine of phi. Restoring torque is there, so we put a minus. Okay. And this phi is very small, therefore we can say that our sine of phi is equal to approximately phi. Therefore we get the restoring torque will be equal to minus L by 2 m G effective times phi. Now we can find out, because the rod has a tendency to move now because it is not in equilibrium. Therefore, we can write the equation of the motion. And for that, we are going to write the first of all the moment of inertia. So we can write our equation of motion, and for that we require the moment of inertia, and the moment of inertia, the rod is going to pivot at one of its end. Okay, so we can say the moment of inertia of a rod pivoted at one end. Well, let us suppose that is of I is equal to 1 by 3 ml square, and therefore we can write the rotational equation. Rotational equation will be our I phi double derivative is equal to our torque, and we already know I as well as torque. So I is our 1 by 3 ml square phi double derivative, and torque is our minus L by 2 m G effective, and this is multiplied by phi. Okay. And here this m and m square, m and L goes away. Therefore, we get from here that phi double derivative is equal to, or we can write it in the standard format of the equation. This will be a plus, and we get this as 3 by 2. This will be L G effective phi is equal to 0. And this is our equation of our SHM, which gives a double derivative plus omega square phi is equal to 0. So from here we can write that our omega square is equal to 3 by 2 G effective divided by L. And we can also write this in the form of our G and A. So this will be coming as 3 by 2, and our G effective is our G square plus A square and square root and whole raised to power 1 by 2. We can also find out the time period. So we can say our time period will be equal to 2 pi, and this we get as 2L upon G effective and its square root. Or in terms of G and A, we can write this as about 2 pi square root. This comes as about 2L, and here we have our 3 G square A square and its square root. Okay. So this is our time period as well as our angular frequency. Next question. It states that a truck is initially at rest with one of its door fully open as illustrated. The truck starts accelerating forward with a constant acceleration A, causing the door to swing shut. The door is a uniform solid rectangular plate of mass m, height h and width w. Neglect the air resistance. So based on this we are having two questions. First is find the instantaneous angular velocity of the door about its hinges when it has swung through 90 degrees. And part B, calculate the horizontal force exerted on the door at the same instant. So here we can just draw. This is similar to the previous one, except that here the door is, you can say, at an angle of 90 degree with respect to truck. So we can say, let us suppose this is our truck. It is moving with the acceleration a in the forward direction, and initially its back door is completely open. Okay. And this door has a tendency to close. And okay, width and W. So here also, as it is moving in the forward direction, we can say there will be a pseudo force that will be acting on the door. And let's assume that at any given moment, this door is at an angle of theta from its original position. And this MA will be the pseudo force acting in this direction. And we can divide this MA into two components. So first component, I have a second component. So we have theta, this angle will be also of theta. So we get this as our MA cos of theta, and we have this MA sine of theta. And therefore we can say that our torque, which will try to close the door, we can say that at any angle theta, the instantaneous torque, we are only talking about instantaneous because this truck is continuously moving. Okay. So at any angle theta, the instantaneous torque and that torque will be trying to close the door. And that torque, let us suppose our tau, will be equal to our force, which is our MA cos of theta, and the lever arm, that is our W upon 2. Okay. So this is the torque which is going to trying to close the door. Now we can use the work energy relationship, because we are supposed to find out the angular velocity, and that we can use our work energy relationship. So finally it states that this is swung through 90 degrees. So it means if it swings through 90 degrees, this door will be closed completely. So this value here, theta is equal to 0, and at this position our theta will be equal to 90 degrees. So when it is completely open, theta is equal to 0. When it will be completely closed, theta will be equal to 90 degree. And we can say that using our work energy equation, we can say the rotational work done by the torque is equal to the kinetic energy gained by the, or rather rotational kinetic energy gained. So we can say that rotational work done by the torque will be equal to rotational kinetic energy gained. And for our work done, we can write our tau d of theta will be equal to kinetic energy is our half I omega square, and the angle is going to vary from 0 to pi by 2. And this moment of inertia of this rectangular door about the vertical hinges, which is our I. So you can say our moment of inertia of door about vertical hinges, which is our I, and this I will be equal to our 1 by 3 mw square. So we simply substitute it, and tau we already know is our ma cos of theta and w by 2. So we get this as, let us calculate this part. We have 0 to pi by 2 tau d of theta. So we get this as 0 to pi by 2, and we are having this ma cos of theta multiplied by w by 2, and cos of theta is the only, and here left is d of theta. So from our cos we are going to get this as sine, and that will be sine pi by 2 minus sine 0. So that will be obviously equal to 1. Therefore we get that maw upon 2, and we can equate this part. So we get this as our maw upon 2 is equal to 1 by 2, moment of inertia is a 1 by 3 m omega square, once again, sorry, this is w, width, not omega, w, okay, and this is also w, width, and here also this is a times width, and we get this as our this will be our width, and we have our omega square. So our mass 2 and 2, and w goes by this square. Therefore from here we get that our w square will be equal to 3a and divided by w, or we can say our omega will be equal to 3a and w its square root. Okay. So this is the instantaneous angular speed when the door is our, what was asked for, swung through 90 degrees. Okay. And we come to our part B, horizontal force at the same instant. Okay. So we are going to find out the horizontal force, that is our part B. So we have our part B, which means horizontal force at theta is equal to 90 degree. So in this case the hinge is, or we can say hinge reaction, should be able to provide the centripetal force so that the door keeps on moving in a circular path as it is bound to close, and also there will be a forward pseudo force reaction. So we are going to have two forces that will be provided by the hinge reaction. So we can say that our horizontal hinge reaction must provide two things. First is our centripetal force, and this centripetal force is making sure that the door is bound to close and it is going to follow a circular path. Okay. So we can say keeping the door's center, center of mass moving in a circular path. Moving in a circular path. And the second one will be forward pseudo force. Forward pseudo force, and that will be equal and opposite to MA. Equal and opposite to the original pseudo force, that is our MA. So it means the total hinge force will be equal to our centripetal reaction plus pseudo force reaction. Pseudo force reaction. And this we can write. Okay, so now let's find out what will be the velocity and the acceleration of the center of mass, and from there we can calculate the centripetal acceleration and other parts. So let us find out the velocity and the acceleration of center of mass. Velocity and acceleration of center of mass. Okay. And our door, the center of mass is going to trace a circle of radius r, and that r will be equal to W upon 2, where W is the width of the door. So you can see that the door's center of mass traces a circle of radius that radius is r, and the r will be equal to w upon 2, where w is the width which is given to us. And we can also find out the linear velocity. Which is nothing but velocity of our center of mass, and that is equal to our omega times r, and our r is w upon 2. Omega we just calculated is our 3a divided by w. 3a and w and its square root. And we can write this as our, this will be coming as our 4, and this will be square, so this we get this as 3a w square root. And our centripetal acceleration, that is called A of c, will be equal to velocity of center of mass square divided by r, and which we just calculated. So this is a square, so we get this as 3a w upon 4, and r is our w upon 2, and here w and w cancels out, so w 4 goes by 2, so this comes as our 3a by 2, 3 by 2 times a. So this is our centripetal acceleration. Now we come to our force components. So we have our force components, and we have a pseudo force, that is of ma, which will be acting backwards on the center of mass. Let me draw it here again. So this was our truck moving towards the right side with the acceleration a, and we were having a door, and if this is the center of mass, so we are going to have a pseudo force at the center of mass, and this height will be equal to w upon 2. Okay, total width is given as our w. And so this, the hinge, because there is only the force which is acting, if I draw, this is our x axis and y axis. So along the negative x axis there is only one force, and there will be a hinge which is, it should be rather be applying a force which is equal to our ma and in opposite direction. Okay. So that will be our reaction force in this direction. Okay. And so we can write it, we can say that we are having our pseudo force and the pseudo force ma acts backward or we can say backward, or we can say to the left on door's center of mass, and therefore we can say the hinge is nothing but the joint, okay, which is this one. The hinge must also provide the centripetal force, must also provide, or we can say exert rather, must exert equal and opposite forward direction MA. Forward means towards right reaction, and that direction is our nothing but our MA. Therefore, the hinge must also provide the centripetal force, okay, because it is also going to rotate, okay, because it will try to close something like this. So this hinge should be also our acting centripetal force. We can say the hinge must also provide the centripetal force. Centripetal force. Let us suppose we call this as a FC, and which will be equal to mass into centripetal acceleration, and centripetal acceleration is our 3/2a. So this comes as our 3/2 m times a. Therefore, the total hinge force magnitude, so you can say our total hinge force magnitude, let us call this as F. So F will be equal to our this MA plus our centripetal FC. So we get this our F is equal to our MA, and FC is our 3/2 times MA, which gives us 5/2 MA. So this is the hinge force that is required. Next question. So in this case, it states that a pendulum is initially at rest with its bob pointing directly toward the center of the earth. The support of the pendulum is then moved horizontally with a constant acceleration A, causing the pendulum to swing. Neglect the rotation of the earth. Consider the motion of the pendulum when the pivot moves over a small horizontal distance d, which subtends a small angle theta naught, approximately d upon re, which is much lesser than our 1. At the center of the earth, radius is given as re, is the radius of the earth. Show that if the period of the pendulum is t is equal to 2 upon pi re upon g, the pendulum will continue to point towards the center of the earth, provided the terms of the order theta naught whole square and higher are neglected. So this is the basic question. So first of all, let us draw an approximate figure for the given question, and we are given an earth. So let us draw so this is our earth, and this is our center of the earth. Its radius is given as our re, and we are having a bob, and suppose this is the pivot point of the bob, and the pivot point of the bob is initially right at the, you can say, vertical. So let us call this as pivot point of the bob, and it is given, it is rather stated in the question that if we move this pivot point through a acceleration A, such that this bob is making an angle of theta naught. So let us once again, we are going to have this will be our RE, okay, and the new position of the bob will be somewhere here, and it will try to move in a circular path like this. So we are going to have, this is our acceleration A which is being provided, and with the help of this vertical it is going to have some angle, we can just say that, and we are having